All right, so it's episode 9. It's actually, I think it's episode 10, 11, 12. This is actually episode 10. Let me fix that. This is not episode 9. Because episode 9 was the field trip. Episode 10. So the topics, oh, here we go with the sound again. Still haven't figured that one out. The topics here, we got to talk about the final dinner prep, and it's going to be a cookout because it's supposed to rain all next week, so I don't want to take a chance on that. So we'll have dinner, and it'll be like, we'll talk about that in a minute. We'll talk about complex pulley systems. I have a couple I want to look at. I'm just going to turn this off again. Okay. We'll do mechanical advantage on machines. We'll get in more on work, compound machines, dot products, integrals, and maybe at the end we'll get a little torque and cross products. All right. So first, let's talk about what's left. All right. So we are here on the 24th. We have Monday still. It's going to be a regular session. And then I'm going to move this. It was Tuesday, the 29th, but I'm going to move it to Thursday, July the 1st. I was going to leave for Florida on the 30th, and we pushed that back to leave on the 2nd. So that allows me to give me another day or two to plan this this final dinner. And I feel like it's kind of rushed. Monday's the last Zoom, and then Tuesday's the dinner. So in that dinner, or it could be lunch, in that time, I want to talk to you about I have some questions I want you to answer just about the course. We're trying to improve. This is the prototype. It's going to get better. It's gotten better since the beginning, but it's going to get a lot better in the fall. And every semester get a little better. So I want to talk to you about that. I need to know who's coming out. What I'm going to do is I'll provide the pizza. We're talking about now it's not Tuesday, June 29th anymore. Now it's Thursday, July 1st. And I'm not sure what time. We'll figure that out in a second. But I'm going to bring the pizza, and I'll bring various pizzas, depending on how many people we have that's going to go. I'll bring the drinks, waters and pop, whatever. And then you all provide the dessert. If you want, you can bring along a cake or some cookies or something. All right. So first off, I know it's kind of early to tell, but is there a time? It's really going to be the Thursday. Heck, I'm cool with breakfast. I don't care. I'm cool with Thursday breakfast, Thursday lunch, or Thursday dinner. And it's just going to all be about your schedule. What works best for you? So in the chat, if you can write in there, if that Thursday works, and if it does, what works best for you? Morning, lunch, breakfast, lunch, or dinner? I go any way. We could all meet for coffee. It's fine with me. And then I'll buy your coffee and I'll buy your muffins and all that. So in the chat there, I'm not sure. Yeah, you may not know yet. But I'll send you all an email. And I've sent you an email before, but hardly anybody responded. So you're going to have to respond to these emails. Right, so I know you don't check your email all the time, but since we don't really, I tried to do the group me, but nobody, I don't know, somehow I messed up. Either I screwed up or nobody just responded, or you guys aren't used to group me. I don't know what it is. Okay, so you all are saying Anthony's not sure. Jacob says any of those times should work for him. And Adam says anytime Thursday works for me right now. Okay, so try and hold open a spot. Now, give me your druthers. Since you're here, you get to run the show. Would you rather do a breakfast, a lunch, or a dinner? Right in there, breakfast, lunch, or which one do you want to just put in the chat? Which one do you want to do? Breakfast, and I'll take a screenshot of it. breakfast, lunch, or dinner. And so the whole thing will take about 45 minutes to an hour. Depends how fast you eat pizza. Do you have a, well, commit to your first choice. Or maybe put them in order. Breakfast, lunch, dinner. For me, it'd probably be dinner, lunch, breakfast would be my preferences. But first choice would be lunch, okay, for Adams. So lunch is good for me. And if it's pizza, it doesn't matter. There's no difference in price, really. So it probably won't be, okay, so Jacob's going for the lunch thing. It probably won't be outside. We may have to eat, like go to Mazzio's or something. We'll find a cool pizza place in town. Maybe we'll go to the top of that pizza place on Campus Corner or something. Okay. So, yeah. Yeah, I think I'll try and make it a neat, kind of a cool pizza joint. Right now, I'm thinking that, that 4-story building on Campus Corner. You could go on the roof if it's sunny or if it's not raining, and if it is, we could eat inside. So right now we're thinking that pizza place, and right now it's looking like lunch is what you guys are saying. Okay, and Carson, you could jump in here too. We moved the final dinner the final meeting from the 29th to the 1st of July. And so instead of being a big cookout, because there's a good chance it's going to be raining, I'm going to go with pizza and drinks, and then you all bring the dessert. But the question is where? And we're thinking lunch, sometime lunch on Thursday. Okay, I'll put that out there to everybody else and see if whoever replies. And I want you to fill out a couple of questions, write in a couple. I'll bring you some pencils and stuff, and you're going to write in just so we can kind of get a feel for. It'd be good to get some quotes and your thoughts. All right. So that's a coming. I'll talk about it a little more Monday. We'll have it more solidified on Monday. All right. So last time we talked about AMA and IMA, and AMA is like the efficiency of the machine times IMA gives you AMA. And then I was going to show you this one. This one we do in class, but it's hard to kind of get a feel for it just with a picture. So we can't really demonstrate that one, but let's look at something like this. I drew up some cartoons here. Now, I want you to, looking at this, I want you to figure out what would the force be, what would the tension be in the green rope, the red rope, and the purple rope. This is a weird situation. You go, how does it even work? Well, it works. We've set it up before. But say you had 100 pounds. Well, obviously, if that's 100 pounds, then the tension on the green rope is going to be 100 pounds and 100 pounds, right? Because remember, the rule is as long as a pulley is massless and frictionless, that the tension throughout a tight rope is the same. So that's fine. So we get the 100. Now, what's going to be the red? You can say it or you can type it. What's going to be the red tension? Uh, 200, right? So that's 200 pounds. And then finally, where you're going to pull down, what's going to be the purple tension? Assuming that the force is above and below a pulley have to be balanced. So if you got 100 pounds pulling up on that, must have 50-50. So below we got 50 pounds. So this would, with this system, you can pull down 50 pounds and it'll lift 100 pounds. And maybe you want to offset the pulleys, that kind of thing, because it's over something. And so you don't want to be right below it. So this might be a way of doing that. Okay. Now, the other thing is that this is a system. And so we put so these forces are all either internal or external. And so we put a dotted I'll show you that. I have it drawn up here. So what we do is, this is the same drawing, but we put a dash, we highlight the machine. So everything in purple is the system. This is a 2-pulley system. Every internal force in that system cancels. Everything else is external. Okay, so this tension here in this rope, this will cancel itself. Okay, now let's try one more of these. Now the green rope again, would have 100 pounds, right? No, it wouldn't. Hello, I'm not thinking very clearly. So what would be in the green rope? Yeah, so maybe Jacob already wrote that in there, but it's 50 pounds on each side. What's going to be in the red rope? This was actually a question on an AP exam where they had to use this pulley system. Then it was hooked up to a lever, and then it was hooked up to a wheel and axle, and so it was a compound machine. And we'll get to that towards the end. So this was what would the red rope be? Yes, 100. So no, it would not be 100. Sorry. What would the red rope be? I'm pulling down with 50, so I got to pull up with a total of 50. So what would the tension of the red rope be? And see, this is no longer a simple pulley system where you just count the number of load-bearing ropes. Now you have to play the game with each pulley. Okay, no one's yet answered correctly what the tension of the red rope would be. You can say, maybe you did. No, you can say it or type it. Going once. Tension in the red rope. The rule on these complex pulley systems is the forces below a pulley equals the total of the forces above a pulley. So on this pulley right here, you got a total of 50 pounds pulling down. So this is going to be just you isolate. I know what you did there, Anthony. But you isolate this pulley right here. You isolate this little system. So you let me see. I can actually cut this out. Let me cut this out. And that's all you care about. You don't care about the rest of the system. So I take it apart. Let's pull this over here. And I just look at it. And so with it, I have in my mind, my mental scissors, I have 50 pounds pulling down. So what do I have pulling up on each? What must I have pulling up on each? If it's equilibrium with each pulley. There you go, 25. 25, 25. And so that's 25, 25. Now, I know what Anthony was doing. He was saying, well, look, that red rope goes around. It's really kind of like 3 sections of it. So you divide by 3, but that's not the case here. You don't do it that way. So you follow the red rope all the way around. Now, in a problem on a test, I'm not going to give you a test on it, but what you'll see in the future is they won't color code the ropes for you. And sometimes it gets kind of with block and tackle. Sometimes it's a block and tackle, and it gets confusing as to what rope is what. Anyway, so that's 25, and then we get to the purple rope. So this is attached to the ceiling. What's going to be that force? Yes, 50. So that's 50 pounds. So if I now go back and pull it out of the oven here, this is where it's done. So I have, that's the same system, but you go ahead and put a dash line, I colored it in, around the system. All the other forces are external forces. So now let's go back and look at this. So the rule is that on the whole system, the external forces down must cancel the external forces up. All internal forces must cancel. All external forces must cancel. Because the whole system is still, the whole machine is still static, right? So if I look at this externally, externally, what do I have? I have going down, I have, let's go with another color here. We'll go with red. No, we'll go with blue. So going down, I have 100 pounds there plus 25 pounds there. So I have a total of 125 pounds pulling down on this complex machine. Up, I got to have 125 pounds. Well, I get 50 from this, I get 25 from this, and I get 50 from this. So 125. That's the way you can check your work on these. If that doesn't work out, you made a mistake. Okay, enough of that. I wanted to go back and hit it at least once. So now we're going to talk more work again, and you've seen this the third time you've seen this thing. Dot products. We talked about first class, second class, third class levers. Talked about a fingernail clipper being a compound machine. I looked it up a couple of nights ago and saw that the fingernail clipper was invented in 1875, which is cool. But what the heck did they do in the Civil War when they wanted to clip their fingernails? I don't know. Okay, and then we worked this problem at the end. I wanted to point out that this key is on the Facebook group. It's problem 5 we did. We also talked about 6. We talked about 7. And then today we'll talk about 10. So that key, though, is on the Facebook group. Review. I don't think I want to go over all these stuff. But the thing, I went back and found these from last summer. I went back and what we were talking about, I've gone back and last summer did a bunch of detailed captions. And so I'm going to include those. Not that we're going to talk about it all night tonight. We're not. We're going to move on. But I wanted to include those because that's better than what I'd put on last time. So I'll add some better stuff on here. Talk about thermodynamics and more details. This was during COVID and I was bored. So I did a bunch of these captions. Okay. And so I'll in other words, if you're still struggling with this idea of dot products and work, I'm going to help you out. If you'll read this, it'll be up either later tonight or tomorrow morning. It'll be up on the Facebook group. I'm going to skip this for now, except that it's just the same idea that I have all these details on work in the orange and yellow captions. And so I'll include those. Also, we briefly mentioned that work is just another suitcase. It's now the biggest suitcase we have. Work and energy suitcase are the same. Work and energy are mathematically the same. We say joules for the units of energy, but a good purist physicist would never say joules for the unit of work. And I see textbooks doing it, which drives me crazy. That is lazy. Work is a force through a distance. That is Newton meters. When you do work on a system, you either increase or you decrease the energy. Okay, so it's called the work kinetic energy theorem, which we're actually going to show tonight. But there is a difference conceptually. But as far as work equals the change in energy. It's not this doesn't equal energy. It equals the change in energy, and that's a huge difference. It's like saying impulse doesn't equal momentum. Impulse equals the change in momentum. Big difference. And then also, last time, we're talking last week, or was it Monday? Where is it? Yeah, Monday, we did some foil stuff, and I went back and found a bunch of captions, so I'll add these in there. I'm not going to go over foil again. Remember, it's not foil. The O and the L, the O and the I annihilate themselves, and so it's just FLA. But it's what allows us to do stack and molt. So that's the problem we did that's the problem we did on Monday. And here's another problem. Here I just took, say you have a force and I give you the force over, it looks like it's over 3 and down 8. And then I give you a change in position over 5 and up 3. And this force, if you can look at the force, as we know, that is not the path. This path probably looks something like, this. It may have started off going up and it ended up coming because these things are curling back on it. It might have been going into the wind, coming up and then coming back, and it ended up like that. That's the path of the object. It would be that red. I sold Adam my iPad and I wish I had the screen back. No, keep the screen, but I got to buy me another screen because this screen is nice and slick, but it's too slick. Don't take that screen off there, Adam, because if you do, well, you maybe already did, but if you do, it's harder to write. Just warning you. Now I gotta go buy another one. I got one somewhere. I'll find it. All right. So anyway, so the point is that when I do the dot product, which is what the work is, which leads to change in energy, the dot product of a force acting over a distance, over a displacement, this would be a draining system, like kind of like that one was too, but this one's going to drain out of the system 39 Newton meters or 39 joules of energy, because whatever this is, that this force here, vector, this kind of greenish yellow, I'm a little colorblind, but greenish yellow vector down, as it's acting over this path, it pulled out 39 Newton meters or 39 joules of work, probably in the form of heat. Probably, it may have been friction. No, because friction is not directional. Well, no, because friction always opposes motion. So this couldn't be friction, but it's something, wind or something acting on it at an angle. Okay, or it could be you pulling one way and it's going another way and whatever. But in this case, 39 joules of energy were lost, which meant that the system slowed down. Whatever this object was, if we keep it simple, say it was a bull running and you're trying to stop the bull. So you throw a rope around it and you're pulling the bull. The bull then has slowed down a little bit, didn't change its mass, but it's lost its velocity. So it lost some energy, okay? Mass times velocity is momentum, but 1/2 mass times velocity squared is energy. So you lost energy here. Okay, and then one more thing on that before we go on to, okay. So I realize this is thermo and it gets a little bit arm wavy. I'll do some solo physics here in a minute. That might help. If we have, this is us pulling something down an incline. Let's go start up an incline. If I'm pulling something up an incline, and we did this problem, one like this a couple times ago, and we found that the mg does negative work when I'm pulling the object up the incline. When I'm pulling, because it's mg hurts me because it's slowing me down. You just got to ask yourself, is this force slowing me down or speeding me up? If it's slowing me down, it's doing negative work, okay? And then if I'm going to pull it down the incline, now gravity's working with me. And so it's actually speeding me up. I could let it go and it'll probably go down the incline. I mean, maybe not, there's tension there, but let's suppose I'm pulling it and so gravity's helping me. So it does positive work. So it comes down to this, when you're looking at it mathematically, if the angle is between 0 and 90 of the force, between the force and the change in position, that's going to be positive work. Actually, if it's between negative 90 and positive 90, all of that is considered positive work. If it's between 90 and 100 and 270 degrees, this time it's one of the few times we don't just look at the reference angle. With work, you have to look at the entire angle. In fact, it's the only time this year that's happened where I can't just say, the drawing will tell you which quadrant it's in and then use the reference angle, sine, cosine, tangent. Here, though, you have to say, wait a minute, the distant, you know, it's because these angles can be obtuse, as it is here. That red angle is obtuse, right? So in that case, it is negative work. And so anything between 90 and 270 degrees, if the force between the force and the change of position, that's negative work. That's draining your system. Okay. So one of the reference sheets that I've added to the, we're up to slide 28. I actually have up to slide 35 done, and I'll get those up. I guess I'll throw them all up there sometime this weekend or something, so that the last case we can look at we can at least look at them all, because I got to get into torque, we got to get into this power, things like that. Might touch on power tonight. All right, so, but just to show you what's on this one, here's the idea of work. If you're going to graph work, let's say, hold on. Let's say we have a force acting over a change in position. So we've talked about the vectors, but here we say, let's say we have a force, it's a variable force, and this force starts off in this first part of this graph. This force starts off increasing with position. So it's gaining, it could be, maybe it's something where the force is increasing linearly. Maybe you keep pushing on the gas, you're giving more and more force as you go. Then the force is constant for a little while, and then you're starting to peter out. Okay. And then at some point down the line, maybe it's a mile away, now you start to actually, either friction starts to take over, or you go up a hill, and now there's overall negative work done on the system, and that's going to put you down in the fourth quadrant. So the area, the force versus position, the area, and we're going to talk about this quite a bit here in a little bit, the area under the curve, that is the work done. In calculus terms, you would say the integral of that change in position, over that change in position, the integral is the work done. So the area of this orange area here, that's doing positive work, meaning that I'm pouring energy into the system for the first, whatever that is, 100 meters, whatever it is, mile. I'm pouring work into the system, and I'm speeding it up. And then I end up taking work, I'm pushing on the brakes, I'm adding, which adds more friction, or I'm going up a hill. Somehow the wind now is starting to affect me. So now I'm overall getting negative work, which means I'm slowing down. If we go to that situation, you go to kinematic situation, I'm slowing down in the last part. So overall, you can look at the work done in the overall system, and you say, well, it looks like I did a little more negative work than I did positive work. So say that's 2 miles. We're going along for 2 miles. Then if I'm overall, you can take the positive area minus the negative area, and you would get how much energy you lost in your system. This is thermodynamics, thermo. I don't want to get into this too much. Here's a couple of examples. I'm just going to leave this. These are on the reference sheets if you want to look at them. This one's weird because you're going backwards. Let's not even worry about that right now. We spend a day on that kind of stuff in class, but let's just not worry about it. Okay, so now solo cup physics time. If I don't destroy, let me go back to full screen. Hold on. Stop sharing. All right. So here we go. I'm nervous. I'm going to spill water everywhere. I look for color. We don't have any colored water. Stupid in this house. So we're going to have to go with clear water. Okay. So this is a little tricky here. All right. Now, solo cup physics. This water represents the energy I'm putting into a system. Here's my system. Okay. Now, if I have no friction, no wind, no air drag, like in free fall, right? In free fall, I'm putting energy into my system because gravity is doing work on the ball. Now, free fall by definition means no air drag on the ball. So in that case, it is perfectly free fall. In that case, I don't lose any energy. I just gain energy, which in the form of velocity. Okay. But let's say there is some air drag on it. Then I pour my work. You can't see that's all this is a reservoir down there. So now I pour work by gravity's pouring work into the system. And look at this. If you can see the bottom of that, some of that's draining out because I'm losing energy. And that's in the form of heat. Usually it's friction. This is not bad though. I mean, that's not a bad system. A car is much worse than this. You lose it because of friction. You lose it in terms of heat, and you can't maintain that energy. If you take your foot off the gas pedal, your car will still go for a little while. And this would be an extremely efficient car. It would go for quite a while, but it keeps losing energy. Okay, so you get that idea. All right, now let's try it again. All right, this time I have a system where, let's say, or you could say that first situation was me dropping something on Mount Everest, where it's going to end up hitting the ground pretty fast because there just wasn't a lot of air drag. Now let's go to Denver, do the same thing, and I'm adding energy into my system, and now it's pouring out a lot faster. All right, now I got a lot of air drag. Or if it's a not as efficient machine, I lose energy pretty quick. If you have oh geez, that's spilling too. Oh, I'm using the wrong one. Oh God, using the wrong cup. Good thing my iPad isn't up here. Oh, that's wet. Hello. Knew I was going to screw this up. Okay. Get rid of that. Oh, what a mess. All right, now I'll pour this in here. Good gosh. All right, now we're going to try it in a system. Now we're like in Oklahoma, okay, with a lot of air drag. Or in a really bad machine, like a car. Now I pour it in, and look how fast it's coming out. So it's work on a system. I'm doing work on a system. I'm trying to speed it up. I got a little tornado there. But the energy is being drained out of the system really fast. So, you have like things you turn, you let them go, and they go about 2 more times and they die. That would be a system like that. Okay. What a mess. Put that there. Get that out of here. I should have brought a towel. Here you go. I got a towel here. Shirt's all wet. Okay. Now, so that is solo cup physics. It does help though to think, okay, I'm pouring energy into my system. How fast is energy draining out? And that was a question on AP test as well. They had like a diagram, a graphic organizer. It had a big arrow, energy coming in, had your system, energy coming out in 2 different places. You had to explain what the system could be. You had to write a paragraph on what would this be. I think probably the best answer was a car with uphill and friction, or a car going along, wind hitting, or air drag, friction, uphill, if you have 3 things draining out. So it's a constant battle, energy in, energy out. Conservation of energy says, the amount of energy ultimately in a machine, you never gain energy. There's no such thing as perpetual motion. And so energy is not gained or lost. It's just transferred into different types of energy, go from mechanical to electrical, and then to movement. But every time you do that transfer, you lose some energy. Okay. So I keep talking about energy and work and forces. Here we go. Now, I make the students do this on a test. This is usually the last test of the year. They have to do the work kinetic energy theorem. And this is has been called the most important theorem in mechanical engineering. I know a lot of you have said you want to do mechanical engineering. Well, this is it. People have this tattooed on them, this work kinetic energy theorem. So instead, I don't have I can't just spend the last 22 minutes going over this with you. So I'm going to show it to you. We'll talk about it as we go. So step number one, you start off with the definition of work, force, the summation of forces of a system times the change in position. And then you end up with the work kinetic energy theorem. And that is the work kinetic energy theorem, which says that the summation of work on a system equals 1F mv final squared minus 1F mv naught squared. Now, that 1/2 mv final squared, that is kinetic energy. This is defined in 1852 by Rudolf Clausius. We are sharing, right? Okay. I'm trying to watch the chat, so I'm not, if you're screwing up. Okay, so this is 1852. They said that we're going to call that 1/2 mv squared. We're going to call that kinetic energy. And you know, the first person to come up with this idea was Leibniz in 1720. They didn't actually formalize till 1850, mostly because Leibniz was German. And Émile de Châtelet, who was French, in 1740s, purported this idea. They didn't understand the 1/2, but they got the idea of v squared, the idea of squaring the velocity. Okay, so this is the work kinetic energy theorem, which a pocket version of this, and we're going to get to these steps in a second, but a pocket version is this: summation of work on a system by forces is equal to the change in kinetic energy, capital K. Now, lowercase k stands for a constant, a generalized constant. Cursive k is lowercase. Cursive k is Hooke's, stiff, the Hooke's coefficient of like how stiff a spring is. So it's in the that's in the Hooke's law. And then there's others, capital K, capital cursive K, that's kappa. That's for torsional springs. It's not a torsional spring, which is a wire that you twist back and forth. So all these K's, you gotta be careful you do your K, but a capital K, it's not KE. Now, middle school textbooks will call it KE for kinetic energy and PE for potential energy, but any college physics book or engineering physics book would say capital K for kinetic energy, capital U for potential energy, capital U. All right. So, and that comes from the Latin. All right. So let's go through this and see how we get from that equation, just the definition of work, to the work kinetic energy theorem, the most important theorem in mechanical engineering. I mean, somebody changed their mind on that. You can't. I mean, that is it. Mechanical engineers are studying work. They're studying how we're losing energy. How can we reduce the friction? How can we stop that on that solo cup? How can we get less water pouring out? What can we do? Ball bearings, motor oil, what can we have a better motor oil? Can we use different kinds of lubricants? All right. The best lubricant they had in the late 1800s to reduce the amount of friction pouring out of a system was pale whale sperm. And they used to, that was extremely expensive pale whale sperm. They would get the blubber and all that when they went whaling, but they would always get that and then store that, and they could sell that for a lot of money because it was really good lubricant on machines. That's one of those little factoids that get stuck in your head. You go, why do I know that? Oh, well. So now let's keep going. We're going to go ahead and rewrite force as mass times acceleration. Now we substitute, this is step number 3. We substitute that in and then I'm going to put the A and the delta X together. Then I come in with the third orange equation. Now, Carson isn't what I'm talking about, but those that have had me know, and Carson will learn this next year, this will derive all these. This is the third orange equation for kinematics. I want to rewrite that delta x as this. Oh, sorry. I want to eventually rewrite the delta x involving velocity. And so I say, okay, a delta x then, this a delta x part is the same thing as, see that a delta x, these two kind of match up. So a delta x from the third orange equation is v final squared minus v naught squared. I substitute that in for that, and I have boom, and then I distribute the m, and I have the work kinetic energy theorem. So it's not a hard derivation, but it's extremely powerful. Okay. So I keep talking about work, and there's the mathematics behind how I can say that work and energy. Notice that work is not the same thing as energy. It's the change in kinetic energy, which I agree does change potential, but you never talk about potential energy in the same breath as work. It's always kinetic energy, you know. All right, so here's something else I want to talk about. We've done derivatives, and we need to talk about integrals now. So we're going to spend the last 16 minutes or so talking integrals. Let's see. Yeah, we're going to talk integrals here. And then we'll get into compound machines next time. We'll get into torque, finally, a little bit of torque. We'll get into matrices and cross products. I'll try and hit the final episode of this summer series with a high note. All right, so derivatives we know is the slope, basically. And, you know, really slope is the $5 word. The $60 word on that is gradient. You read these articles. I was reading an article on, there's something in, it was this weekend, and it was in the idea of flow, and it was in electromagnetics, and it was talking about gradient. So they don't even use the word slope. They're using gradient. Gradient's better because when you have two-dimensional, three-dimensional objects, gradient is like slope is a two-dimensional line, right? And it has a rise over a run. Okay, boring, boo. Gradient is like a mountain, and depending on what part of that mountain you hike up, there's different gradients, right? And so, but the gradient is the gradient field is how the entire mountain is changing. So if you look at it in 3 dimensions, you go, oh, I see over there, it's like cliffy, and or say you're skiing. This area is the green slopes. That area is black slopes, but gradients, it's called gradient operators when you get into 3Ds. And so it is still derivatives. It gets into what's called partial derivatives, but it is still the same idea. It's still kind of rise over runs, how it's changing. And so we've done derivatives in class. This one we know has no slope, there's derivative 0. This one happens to be force. Daggone it. Okay. This one happens to be force versus time, and the area under there is impulse. This is a really good, I'm proud of myself on drawing this one. This one is force versus position, change in position, and the area under that is work. This blue area is work. Okay. So we're going to look at both of those ideas. They both involve area, which is the same thing as work, which is the same thing as the integral. So for the derivative, it's how much it slopes. And we've done that. Let's keep going. The new thing here is work. So integrals, so derivatives are, power rule, right? Power rule. Well, when you do integrals, you're doing what's called antiderivative, or you're doing it backwards. Now, I know Jacob will be in Aegis next year, and some of you are going to be in calculus. And in calculus, if you're in AB, you'll spend the first semester on derivatives and the second semester on integrals. If you're in Aegis as a junior, pretty much you'll touch on calculus. And then as a senior, you'll hit it hard, I think. You'll do some derivatives second semester. If you're in BC calculus, you'll be doing integrals in the first semester. It goes a lot faster. But I would say that 70% of calculus is integrals and about 30% is derivatives. Calc 1 is derivatives and partial derivatives and integrals. Calc 2, Calc 3 in college, pretty much all integrals. All right. So the basics of integration is if you have some kind of function, you take the antiderivative, and that's the formula right here. Don't worry about this. We're going to move on, but that's the formula. If we could we'll spend a day on this in class, but we're just on the time right now. That's how you get. So if it's like it's x to the 5th, this would be x to the 6th over 6. Because what you're saying is if I take the derivative of that, the power rule of that, I'm going to get that. So you can say, so antiderivative is you do the opposite of the power rule. Okay, so to subtracting 1, you add 1. See what I'm saying? And the A and the B are the boundary conditions. This C, the C there, that now in math, they would call it capital C. In physics, we would say that is X naught, or we integrate basically over position, or it could be time. I forget, I didn't include that. T naught, or T initial, which is normally 0. But we integrate over position, we integrate over velocities because of the work kinetic energy theorem, and we integrate over time. I don't know of any formula that integrates over acceleration. There just isn't any. But those are the 3 main ones you're going to, all through your college career. Yep. Those are going to be the 3, mostly the 3 you'll integrate over. Okay. Maybe there's some other few weird ones, but that's probably going to be it. Okay. So we'll get to the integral. I want to explain the integral here in a minute, but here's a problem that I was hoping we had time to do. I don't know. We don't have time to work the whole thing, but let me go over with you, and I'll put this in the screenshots. So here we have a variable force acting on a 50 kilogram. This is a question that I've had on when I teach AP physics. This is in the AP physics, my AP physics tests. I'm not saying it was on the AP physics exam, but it's in my tests in my class. So here we are. A variable force acting on a 50 kilogram object drops off linearly from a maximum of 450 newtons to a minimum of 300 newtons over a 80 meter displacement. Okay, so I start off pushing on it with, or the machine's got, say it's a battery that's starting to run out of juice. Say it's an electric car, and initially it's putting 450 newtons on the car, and by the time you get through your 80 meters, about close to a football field long, it's down to 300 newtons that it's putting into the car. Okay, because it's losing all its juice. Okay, so the question is, how much work is done actually the question is, if the object is moving at 15 meters a second at the time the force first encounters the object, okay, then this battery kicks in, but it's losing juice quickly. How fast is the object moving at the end of the 80 meters? You see that? So you go, what the heck? What do I do? Well, anybody want to suggest a start? A starting point? What should we do? There's a efficient way. There's all kinds of ways to solve this, but the most efficient way. Anybody got an idea? Hold on. Okay, I thought you were on mute the whole time. All right, anybody got anything to say on this one? Clarification, questions? What's going on? We're trying to solve the problem. We're trying to see how fast. This is obviously not a real car. It's only 50 kilograms. Let's say it's a robot. And yeah, so it's a robot moving along, rolling along here. And you want to know how fast that robot going to be moving at the end of the 80 meters. Okay, pretty fast robot. I mean, it's moving at 15 meters a second to start off with. The fastest a human run is 10 meters a second, right? Okay. Well, having done this problem a few times, the fastest approach to solving it, if you're on a test, is to go to the graph. So we go to the graph and we graph the daggone thing. We start off at 450 newtons. We end up at 300 newtons after 80 meters, right? It didn't talk about how long it took. That is a huge concept. The time is not a part of work. Time is part of what's called power, and power is work divided by time. If we don't happen to get to that, it's on your next reference sheet, but power is work divided by time. So we're not talking about horsepower here. Work is pure change of energy. So it doesn't say, did it take it 20 minutes to do this? Did it take it 5 seconds? Okay, that's the difference between horsepower. Anyway, so the fast way to solve it is to just find the area. So we find the area under this curve here, and we get that 1/2 base times height, 1/2 base 1 plus base 2 times height, because it's a trapezoid. And we end up with an area of, well, there's my work for that. Okay. And then we go on and we say, okay, that area ends up being 30,000. Okay. Then that is that work. That's your work. And that's equal to the kinetic energy, the change of kinetic energy. So it's 1/2 mv final minus 1/2 mv naught. And you then solve. You know that you have the object is 50 kilograms, so you know the mass. All I did there was I isolated the V final in my system, and then I just plug into this equation and I get my answer here. So my final speed is 37.7 meters a second. Now you could have tried to do this as work using vectors, some kind of free body diagram, found forces, count those forces, found acceleration, then from that acceleration, which would have been difficult, then find from the accelerations, find the, using say third orange, you could then finally come up with the final velocity. But it would just take us a lot longer. This is much faster. So work kinetic energy theorem will solve a problem. You'll spend 5 minutes on it. The kid sitting next to you in class will spend 20 minutes on it. So it's a beautiful equation. All right, so now I'm down to about 5 minutes, and I want to talk about what's in this box. Okay. So let's take a look. I've been hawking this for months now, and look what the box is full of. It's full of little blocks. Ha! I had to go buy these. I was going to start. I started to make them, and man, these aren't easy. So these are really perfectly the same wooden blocks. So I'm going to use this, and I demonstrate this. Basically, I'm going to put these blocks together and talk about integration. Okay, here we go. So integral calculus, you're trying to find, like, for instance, impulse is the integral from T1 to T2. That's my boundary conditions of some function. That's this crazy curve here. With respect to, this means with respect to that dt, that little dt, with respect to time. Okay. So in other words, this is what's on, this t is on the horizontal axis. This f is on the vertical axis. So it's this f versus t. And the integral then, integral calculus, as Newton figured out and Leibniz at the same time, we use Leibniz notation. Leibniz used this for the integral because it really did. I always thought it looked like an elongated S. That's what he said. It's like summation of a continuous function. Okay. So let's say this block here, we're going to plot force. Let's say in this case, we'll do this as impulse. So we're plotting force versus time. So this little block is going to represent, each block will represent 1 kilogram meter per second. That's the resulting change in momentum, because impulse is the same thing as change in momentum. So when I put a force, if a force acts over time is going to change the momentum of an object. Okay. So this would be a case where 1 Newton of force acts on an object, a 1 kilogram object for 1 second. I would have this much change in momentum. Now, the height of the block then is the applied force. The width of the block down below is the change in time. I wrote this all last summer, and I've never had a chance to actually teach this. So this represents the first time I've ever tried to teach it this way. I just come up with this idea. I don't know. I dreamed about it or something. I'm down to 2 minutes. 2 minutes. All right. Let's see how far we can get. So let's plot the constant 1 Newton of force over a period of 6 seconds. All right. So I'll do this live here. So if I have this is in this case, this would be 1 kilogram meter per second, because it's a 1 Newton times 1 second. This would be 2, now it's 2 kilogram. That's going over 2 seconds time. And this is a force that's not changing. This is the easiest. Okay, I'm showing you the default, the easy version. So then if I do it for 3 seconds, blah, 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 kind of boring, right? But that is the amount. Okay, you see what I'm doing. Let's go back to, in 1 minute I have left. Let's go back to sharing the screen real quick. I'm gonna go 1 minute over, just 1 minute over. Okay, if I want to get stopped at a point here, and then we'll come back. Okay, so there's 3 Newtons over 3 seconds. There's 4 Newtons over 4 seconds. There's 5, there's 6. Okay, now we have, that's representing 6. So the area of all that put together is 6 Newtons. Okay, that looks confusing. I don't like the way I wrote that now. I just realized that it's the first time I've taught this. But it's 1 Newton being applied. Yeah, I don't like that. Okay, it is, each little block is a Newton second. So it is kind of 6 Newton seconds, but it sounds like I'm talking, I gotta change this. It sounds like I'm saying it's now 6 Newtons. No, it's still 1 Newton. Okay, that's confusing. Nope, bad. I'll change that. But that, I didn't get to integrals. That's just the start. We have this, talk about, and then we'll get to compound machines. And then finally, we're gonna get to torque. Okay. Well, first time you teach something, usually you suck. And I sucked, sorry. But I learned, thank you. Okay, so we're now done, I guess. Tomorrow we don't meet, this is Thursday, so we're not going to meet again until Monday. But I do want you to look at Thursday next week. A week from today will be our dinner celebration that you did it, you made it. I'll give you little certificates, okay? So that you can have those and I'll sign them, so you'll have those as proof. Just put them in a drawer, and then if anybody ever questions you, you can say, yeah, I gave up a good chunk of my summer to learn a little physics. Nobody else did. Well, me and 9 other people. So that'll be a week from Thursday. Okay. Now, last thing here, kind of exciting. A Wednesday of next week, I'm meeting with Darcy Pippins, Melinda Minshall, Dr. Furnett, and we're going to have a powwow. We're the teachers involved in this to determine what we're doing in the fall, because now Darcy's going to offer us a Spanish, Furnett's going to offer a kind of biology, and then Minshall's going to offer French, the same kind of way, but more formal, more with testing, things like that, where you get kind of more credit. So you'll be able to take classes, you and a kid from Godibo or Durant or something could take classes from us, is the idea. Anyway, so I will see you guys. If you guys have a question, stick around. Otherwise, I'll see you Monday, 6:30. Any questions from Carson or Jacob?
Have a good night, Askey.
All right. See you, Carson. Jacob, what do you got? Nope. Okay. All right. That's it. Until Monday.